right. Okay, let's start. So this is the second part of the event series, Build an LLM from Scratch. Last time we went through some fundamental concepts. This presentation is largely based, as I said last time, on the book from Sebastian Raschke. You can find the book on manning.com. The book will be published early next year, but you can already buy it and you can get early access to some of the chapters. And frankly, that's a great book to learn, really inside out, how to build an LLM from zero, basically starting from the text, starting from tokenizing, and then going further into attention mechanisms. And there's also a GitHub repository that you can clone and play with. We'll see it later. So we're going to look at some code example from the book. It's quite well explained. You have also all the graphs and figures there, and you can play around with attention mechanism in chapter 3, or play around with text in chapter 2. Okay. All right, so today we're going to speak about attention mechanism. This is at the heart of large language models. It's quite important to understand, because this is basically how the transformers have achieved such an accuracy in the last few months, right, since GPT-2, 3, and so on. And this is fundamentally different from what we were doing earlier with RNNs, recurrent neural networks. So we'll dive a bit deeper. But before doing that, I think we need to recap a little bit from what we said last time. So very quickly, an LLM is based on deep learning using neural networks. Generative AI is more than large language models. Generative AI is about also generating videos, images, and so on and so forth. Deep learning, machine learning are all subset of artificial intelligence, because there are also other techniques that can be used for mimicking human intelligence, like fuzzy logic, symbolic reasoning, and so on and so forth. But okay, we discussed all that last time. We also discussed last time how we build an LLM. We start with data filtering, data cleaning. Then we tokenize the text, meaning we break the text into smaller pieces. Can be words, can be byte pairs. Then we convert the text, the tokens, into vectors. And these vectors, also we need to know the position of the words in the sentence. So we add the positional embedding to the embeddings. Then we decide on the architecture, decoder, encoder. We discussed that last time. And then we choose a strategy to pre-train a model. All right, so don't want to go too much deeper, far deeper on that today. We just looked at encoder, decoder last time. So a quick summary of what we've seen last time. So I guess that should be okay. Now, in the second part of the presentation last time, we also reviewed how to work with text. That's the first part. If you look here, right, there's the data preparation, sampling, and today we look into attention mechanism. Okay. We also seen that before we can use the text to pre-train a large language model, we need to convert the text into embeddings, or to convert text into vectors. This is not only valid for text, we also convert audio into vectors and videos into vectors to be able to train a model with text, audio, or video. One of the things that's quite fundamental to the large language models and language models in general is the fact that we're trying to find similarities between words and between vectors, and we'll see how to calculate similarities between vectors. But the nice thing about embeddings, once we have trained embeddings, is that you can see that similar concepts or similar words, they will be closer to each other in the vector space. So here are some examples that I'm showing. We showed that we've seen that last time already, so it's just a repetition. And then we've seen last time that I've said that before converting text, you need to convert into token IDs, and then these token IDs you transfer and you convert into vectors. And in order to train a model, you need to have a sequence of text. We know that encoders, decoders, for example, they generate word by word. So you need to give a sequence of words, and then the sequence of words plus one word, and so on and so forth, right? Because you want to train the model to predict word after word. And that's the way how to prepare this data sampling with a sliding window. You can choose if you want to skip 1 word, 2 words, 3 words, depending on what you do. And then you create the token embeddings at the end, and you can start training. So this was just a quick recap of what we've seen last time. So I'm not sure there's any question. I don't see the chat, by the way, so unfortunately, but if you have any question, just speak out. All right. Okay, so next one is really about attention mechanism. This is really the focus of our discussion today, and this is quite fundamental. We've seen earlier that the second step is really to understand how to implement attention mechanism. But before jumping into attention mechanism, we need to go back into the past and understand what we had before the transformers. We had recurrent neural networks. They were used already for translation and text generation. A recurrent neural network is trying to learn a sequence of words, as you can see here, right? For example, it's trying to translate German or English into English or German, depending which side you want to look at it. And the RNN were already capable of doing translation or text generation. But the problem with RNN is that you were losing the context over long sequences. Right? They were okay, but they had trouble with long text, for example. Because in a RNN, right, the encoder is updating a hidden state at each step and is trying to capture the entire meaning of the input sentence. So you would have a long sequence, and then you would really, can you hear me? Okay, yeah, sorry. So the input text would be fed into the encoder. It would then update its hidden state and then fed to the decoder to do a translation, for example. So if you have an encoder with the word kannst in German, it would translate to can. And then the word do would come, and then you would translate to you. And then, unfortunately, the sequence of words is not the same in German and English. Right? So, can you help me? The me, right, in German comes after kannst du mir, which is a different order of words. And the recurrent neural networks, they had trouble to translate in the right order. But we don't need to go much deeper into that. Let's go to the concept of attention mechanism. And the idea of the attention mechanism is to allow us to capture dependencies between words. Basically, to understand how each word in a sentence is related to each other word. And you can see it as we've been talking about word embedding. A word embedding is really coding the meaning of a word in isolation of its context. And in the transformer, the attention mechanism is helping to code the meaning of the word in a vector in its context, in the sequence, because we all know that if I say I like dog or I like hot dogs, right? In the second sentence, the meaning of dog is different than in the first sentence, for example. So if we were using only the embedding of the word dog, then we wouldn't understand really what we mean in the second sentence. The word dog then has a different vector representation depending which sentence is part of. All right. So the attention mechanism is really a way to allow each position, each word in the sentence to attend to all positions in the same sentence, to understand how it's related to the other positions in the sentence. So let's go to the next slide. We will become a bit clearer. So, okay. So let's take a concrete example how it works. So you have a sentence and you don't know which word needs to attend to which. So let's take dog, for example. Let's take dog. Dog is the query vector. That's a convention. So we say, okay, let's look at how dog is attending to the other words of the sentence. So you have to look at each word and query each word against the different keys. The different keys are the other words in the sentence. So you take dog, how does it relate to itself? Dog, how does it relate to chased? And so on and so forth. And at the end, all this will produce an attention map. And in this particular case, you know that chased and cat will be very important words related to the dog when we are translating, for example, but across the street does not really relate to dog, right? So this is how it looks like. And this is showing already the attention layers. So here you can see that the dog here relates to chased because the dog is chasing. The dog is, of course, is related to itself, right? Because dog is a dog. And in this particular case, the subject of who is being chased is the cat, right? So, and you can see that there's not much of relationship between dog and across and the street. So all this will be learned. It's not something that we know upfront, right? We have to train the large language model to understand these relationships between words. And this is the objective of this attention mechanism. What happens is that this attention map captures the attention of each word to each other words. And then when we multiply these values, we will get a context vector at the end. So we will consolidate all these maps together to get a context vector that will represent the context vector of the word dog in this sentence. Maybe another way to look at it, key, query, and values. I've spoken about the key. The key is the word that we're trying to understand the context. The query are all the other words in the sentence, and the value are the final values that we want to produce as context. It's quite similar to database operations or recommendation systems as well. So, for example, in Netflix, if you retrieve a single video, the algorithm focuses on selecting the video with the highest possible relevance score. So similarly, the cat in the sentence was relevant to the dog. If you look at the video in Netflix and you try to find something relevant, it will try to find something that is similar to what you're looking for. The most critical distinction between attention and database operations or retrieval systems that we provide a concept of retrieving that is more abstract. It's more difficult to understand. But we can take it maybe a step further and give you an example here. So in a typical retrieval system, you would have, and these are just examples in Python. Let's assume you have key and values. So the key is apple, and for apple, you get a value of 10. Then for banana, you get 5, and then for chair, you get 2. Now, if you want to get the value of apple, then obviously it will give you 10. But based on this dictionary, if you do a query about fruit, it will not find the value for fruit because fruit is not part of the dictionary. So what we're trying to do is to determine how much attention our query should be paying to each of these values. So we can say, okay, a fruit is 60% of an apple, it's 40% of a banana, and maybe 0% of a chair. And that gives you a value at the end, which is kind of the embedding vector of fruit. So I think that these are different ways to try to understand the attention mechanism. So the percentage at the end is the attention score that we're trying to calculate for a particular word in a sentence. Now, to fully understand the attention mechanism, we also need to get an intuition on how we calculate similarities between vectors. We'll see later that we have different ways to calculate similarity between vectors. But here, for example, you can see, and we've seen that before, you can see that fruits are clustered together, vegetables are clustered also together, and furniture is clustered at the bottom. Now, using their vector representation, we should be able to find out if banana is close to peach because it's a fruit, or it's closer to a chair because, okay, in this case it's not. But so using vectors, we can determine similarities between concepts, between words. And how does it work? That's also something I found interesting. There are multiple ways of calculating vector similarities. We can use cosine similarity, where basically you calculate the cosine between the two vectors. You have Manhattan similarity, you have Euclidean similarity. But in our case, in the attention mechanism case, we will use the dot product, so the multiplication of two vectors. So if we multiply two vectors, what we call dot product, if two vectors are pointing in the same direction, you can see it here on the slide, on the figure, then the product will be greater than 0. If they are pointing in opposite directions, the dot product, the result will be smaller than 0. They are not very similar. If they are exactly perpendicular 90 degrees, the dot product will be 0. Right? So it's neutral. We cannot really distinguish if they are similar or not similar. So using this information, we can define a simple heuristic to determine the similarity between two word vectors. The greater the dot product is, the more similar two words are in meaning. So basically, we're trying to understand the meaning of words and similarities between words, and that will help us to calculate the context vector of a word in a sentence. Good. Maybe there's a question. I don't see the chat, to be honest. Let me see. No question? All right. Okay, let's continue. So as I said earlier, the goal of the attention mechanism and, the self-attention in this case is to compute a context vector for each element, right? So for each token, for each word in a sentence, we will calculate the dot product with each other element. So for example, consider the input text. Your journey starts with one step. So each sequence element, such as x1, right? For example, or x2, x3, they correspond to an embedding vector that represents the word you are, for example, okay? Our goal is to calculate the context vector for each of those elements. And to calculate the context vector for each of those elements, we will multiply each element with each other word. So let me show you here, right? So, so we will calculate some intermediate value for the token 2. So the token 2 will be multiplied by the token 1, and it will give 0.9, and that's an attention score. So your journey, they are closely attended, they are closely related. Then you have a journey with himself, 1.4, then journey with starts, it's 1.4, and so on. These are attention scores. Yeah. This is just computed as a dot product. It calculates the similarity and gives a number. Then after that, in the next step, we need to normalize the attention score. The goal behind the normalization is to obtain an attention weights that sum up to 1. So that if you have different sentences, you always have the same value, same sum that is equal to 1. If you would not do that, then that would be difficult to compare, because then you're using basically different scales. This is very useful also for interpretation, as I said, right? Because you need to have the same kind of scale, and then for maintaining training stability. You need to have not too large values, not too small, and so on. So we have now attention weights. What do we do with these attention weights? Then for each of the for each of the word in the sentence, we will then multiply the word embedding by the attention, by the relevance. In fact, we can speak about relevance. So we will multiply euro by 0.1. Okay, we'll see that here. Right? So 0.1 is the result of the multiplication of the token euro with the token 2, which is journey, that gives a 0.1 normalized. I mean, that gives 0.9 and then 0.1 when it's normalized. So you multiply euro by this attention weight, and then journey by the other weight, then you sum everything together, and then you get the context vector for the query number 2, which is the word journey. So for every word in the sequence, you get a context vector. You get an enriched embedding, if you want. It is enriched with the context. It is enriched because now you have integrated into the vector representation of the word the fact that the word journey is in the sentence with the word your, and the verb starts after that, right? So it's an enriched representation of the embedding, of the word embedding. So in self-attention, context vectors are really crucial. This is what makes the whole difference. The purpose is really to create, as I said, I'm repeating myself, that's quite important, is really to create enriched representations of each element in an input sequence based on all the other elements. And this is really essential. Now, in this example, that was a very simple example without weight. So basically, you cannot train this model here that I'm showing because there are no weights, there are no parameters you can learn. So it's just a multiplication of some vectors, right? Together gives you a weight and give you a score. But you need to train the model, right? Because when you start, you will just randomly initialize the embedding vectors for the words, for example, and if you start multiplying them together, that will mean nothing. So we need a way to learn. But before going to the next chapter, so that's the end result. We have all the context vectors. In each row, you have a context vector. And this is the result of the attention mechanism. You have a context vector at the end, right? And all packed into a bigger matrix. Now the matrix will help to parallelize computations and use GPUs to have parallel matrix multiplications and so on and so forth. But here you can see the representation of a journey. We've seen it before. And as you can see, the second row contains the attention weights that were computed previously. So I can show you quickly. There's no question how it works. It's relatively simple in terms of calculation, but it needs a little bit of thinking to really understand how it works. So here, for example, you have a tensor or matrix. Let's assume the embedding vector is three-dimensional, so you have three values for the word euro, you have three values for journey, and so on. So this is one. Then for each, so we take journey, right, as the query. So this is the first, element 0, 1, so the second element of the inputs. And then you multiply this query with all the other vectors, right? With the vector 0, 1, 2, 3, 4, and 5. So and then you get the same result as before. So you get the first result is 0.9. That's the multiplication of journey and euro. Then you get 1.4. That's a multiplication of journey with himself. Then you get 1.47. That's a multiplication of journey and starts and so on. Now you can do it a bit differently. You get the same result. So now you can normalize the weights. As we said, right now we have 0.9, 1.49, so they are not summing up to 1. So now we'll normalize them, and then we get a normalized form of each of these weights. We have 0.14 instead of 0.9, 0.22 instead of 1.49, and so on. So, but the sum of all these scores are now 1. So they've been normalized. You have different ways to normalize. There's a soft, this is a naive soft max implementation. So a different way to do that. But usually we use torch softmax to normalize the vectors. Now the result, as you can see, is a bit different from the first calculation, but overall, this is quite similar. All right, and then, as I was saying earlier, you compute the context vector for the second row. I think we have the second row here, right? The second row here. You compute it here. Yes, that's the last step. You multiply the input tokens with the weights for each word, and you get a new embedded vector that is the result of the multiplication of the weights and the input and summed together, right? Or the result of the multiplication is summed up together. And that gives the same result as I was showing earlier. So really, it's a matter of multiplying all the words together, understanding how the words relate to each other and how much similar they are to the keys, if you want, and then based on that, you get a value at the end, a context vector. Now, this is a bit of a primitive implementation because we cannot train it. Now we need to have weight matrices. So we have to have trainable weight matrices that will, based on what you want to achieve, right? Based on what you want to predict. So basically in a large language model, you want to predict the next word, then you feed the next word into the decoder again, then you predict and so on. So you want to train in such a way that you can start learning. So what you do earlier, we had just a dot product multiplication between the key and the value. But now you will multiply the key, the value, and the query, sorry, with weight matrix. And these weight matrices, they will be updated at every single step of the training. Okay. So there will be we will be using back propagation to learn the weights. This is based on the derivative of the loss function, but fine, we don't need to go into details. But basically, we need these weights to be trainable. So we will first multiply the query matrix with weight matrix, and then we will also multiply the values and the queries. If you look at the second step, that it's pretty similar to what I was trying to explain earlier. The only difference is that you add the multiplication of the of the key and the queries by a weight matrix, but at the end you also get an attention score. Because these attention score and the context vectors, you need to learn them, right, to be able to predict something. So these weight matrices, they will be learned over time. At the beginning, you will use random values, and over time they will be trained. And these billions of parameters, they will be trained and give you the large language model. And the third step is going from the attention scores to the attention weights. As earlier, we compute the attention weights by scaling the attention scores and using the softmax function as we did earlier. The difference is that we now scale the attention scores by dividing them by the square root of the embedding vector dimension. But okay, that's very similar to what we were doing before. Which the idea is really to help improving the training performance, basically. I can show you later in the code. So if you go down in the code, you have access to the code, right? So if you go down, you have now multiplications by the weight matrix. So you just randomly initialize 3 weight matrices here. So you can see with the dimensions you can choose depending on your vector dimensions. Then the first step is to multiply the query 2. You remember, we are using the second word in the sentence as an example. So that's why we are multiplying x2 by the query, x2 by the key, x2 by the value, and then we get tensors, and then we basically execute the same calculations as before. I don't want to go through that again, but you get the weights, and then you need to scale the weights using the softmax attention. Okay? And then you're done. Then you have the attention layer of a transformer. And then, of course, you can implement it in a nice way using a self-attention class that Sebastian has written here. But this is basically the attention mechanism. I hope I could help you to understand how it works. But the trick is really to understand that we're trying to get a representation of the context of one word based on all the elements of the sentence and how it relates to the other word. And based on that, we get a score. And this score will determine how similar this vector is to others. And then we'll learn, and then we'll be able to generate text or translate. And so on. Any questions? Let me stop sharing. See if I have any question in the chat. No question. Maybe I was either not clear enough or was too much information. Anybody wants to say something? Okay, then in that case, no question.
No, it was all fine.
There was probably a lot of information. I hope I could, in the understanding of the attention mechanism, but it might take some time. Read the book. It's very well explained. You can test by yourself. It takes sometimes to get the intuition, right? To be honest, it took me some time as well, right? Nobody knows better than others. So yeah. All right. Thanks a lot. Next time we'll go to the next chapter if you're interested. And happy to talk about that next time. Thank you very much. Bye bye.
Thank you very much, Patrick. Have a nice weekend. Bye bye.
Thank you. Thank you.
Bye bye.